Hello, and welcome to this session on confidence intervals, with me, Mr. McIver, here at the London Central and North West Maths Hub. This is actually the first of a series of videos working through confidence intervals. It's quite a subtle idea, and this first session is simply going to look at using a point estimate for a mean. Let's look at some means that you might find if you had a look around online. I looked at average heights across the world. Who are the shortest and tallest people in the world? And according to the Snapper website, on average, the tallest men in the world are in the Netherlands, and the shortest are in East Timor. Brits come somewhere around the middle with a mean height of 178 centimetres. How on earth did this survey company get a hold of that particular figure? What they did is they took a sample, and a sample can never give you the actual true mean for a population. All it can ever do is give you an estimate. And because you generally carry out one sampling exercise and work out one estimate for the mean, what you get is technically known as a point estimate for the mean. We're now going to look a bit more closely at what that actually means in practice. And to do that, we're going to look back at our fictional town of Specialtown, which appeared in one of my earlier videos on sampling and statistics. And what's special about Specialtown is that it has a population of 3,000, comprising precisely 1,500 men and 1,500 women. Here is my complete dataset for male heights in Specialtown. The first person on my list has a height of 180 centimetres, and if I scroll all the way down to the bottom, you can see the last person on my list has a height of 162. Of course, in this particular case, I have data for the entire population. But in practice, you never have this data. So it's important for you to understand the relationship between what you will have in your sample and that population that you don't fully know about. So we're going to take a sample of 4 people from that population and use that to calculate our sample mean. And for this bit of statistical theory to work, I have to ensure that this is a random sample from my entire population. How do I take a random sample from a population? Well, the first thing I do is I give each member of my population a number. Number 1, the height 180. Number 2, 166. And so on, all the way down to number 1500, who has a height of 162. What I then do is I use my spreadsheet to generate some random numbers. These 4 random numbers correspond to the 4 data points I'm looking for, and if I hit calculate now, I can recalculate my random sample as many times as I like. Of course, what I'm actually looking for is a sample mean, so I better add on an extra line at the bottom of my table. There you are. My first random sample of 4 has a mean height of 181.3. If I took a different sample, I get a different mean, 187.3. Let's try another mean. 181.3, 176.8, 179, round about the mean for the UK, 178, 176, oh, quite low that one. 185, it's high again. 179, round about the national average. Oh, 173.8, quite low. As I calculate a whole sequence of different means based on different samples of 4, they kind of bounce around. The key question is, do they bounce around a point which is really, really close to the actual mean? Because in this special case I've created, I have the entire population, I can check up on what that true mean is. So let's find out. All I do is type in equals average, and I get a true mean for the population of 178.5. Let's take a closer look at 10 of those point estimates for the mean and see how close they lie to that actual population mean. Here are my 10 point estimates for the mean and my true mean. First, I want to compare each of these estimates to the actual mean. You see, the first one is a little bit on the low side, the next one's a bit high, the next one's low, the next one's high, the next one's low, low, high, 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 high. You'll see that of these 10 estimates, 4 are a bit low and 6 are a bit high. That's pretty close to half of them high and half of them low. Could it be that my point estimates are symmetrically distributed about the true mean? Amazingly, the answer to that question is yes. What is more, if I now take the mean of all my estimates for the mean, I get a figure incredibly close to the actual mean, in spite of the fact that this is a pretty rubbish sample size of 4. And by taking 10 of those samples, I'm still only getting a sample of 40. Still, they average out at a figure pretty close to the population mean. And this takes us on to our first big idea for this session. Provided you take a random sample, a point estimate for the mean based on that sample is an unbiased estimator for the true mean of the population. It's as likely to be a bit high as it is to be a bit low. Right, let's go back to my sampling frame here of 1,500 data points. There's my true mean, 178.5. Here is one of my point estimates for the mean based on a particular sample of 4. You've just looked at a table showing 10 different sample means. But what if I'd worked out a whole load more than 10, say 50? Here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 50 different sample means, all still based on samples of 4. And as you can see, they vary quite a lot. We've got one down here of 170. And if we look down, we'll see there are a couple that drift up to about 184. Now, what I'm going to do is I am going to look at the distribution of these estimates for the mean. We're not talking about the distribution of heights in the male population. We already know that they are normally distributed. What I want to look at now is the distribution of point estimates for the mean based on samples of 4. And here's what you get. Does that shape look at all familiar? Comes up to a peak and drops back down. Looks awfully like the normal distribution, doesn't it? In fact, it is. And that is the second big idea for today's session. The distribution of the sample means is normal, provided your samples are random. That pretty well wraps it up for this session. But I just want to point out one other idea that pops up in the follow-up task. Here is the mean male height plotted out for 50 samples of 4. As you can see, they're centered around, I know that looks like 180, but in fact that should be 176 there, and that should be 180 there. Don't blame me, blame Excel. This is just how it plots histograms. So, yeah, this distribution is pretty symmetrical about the true mean of the population. Look what happens when I make the sample bigger. Here is the plot for 50 samples of 16. Notice the scales are the same. The 176s line up, the 184s line up. They are still bunched symmetrically about the true mean. But you see how the ends of the distribution have come in? We still get a normal distribution, but the spread is smaller. And looking at that in more detail is going to be the topic of the next session. But that just shows you the rather unsurprising fact that the bigger the sample, the better your estimate for the mean is likely to be. For today, the two big ideas are this. Provided you use a random sample from a population, a point estimate for the mean based on that sample is an unbiased estimator for the true mean of the population, and the distribution of the sample means is normal. And amazingly, this is still true even if the measurements in your original population are nowhere near normal. Now, I'd like you to work through the task you've been set.